Hello, everyone, again. This is from Lecture of Cross Products. This is an interesting one. I like this one. Cross products are super useful, especially in my major for engineering, especially dealing with torque and things like that. We use this all the time. But this isn't some interesting stuff I didn't know before. Again, this is just for my study and maybe your benefit as well. But feel free to comment on mistakes I make and or things I should put in here. Okay. First, let's go over the definition of a cross product. It is a vector where if you take y vector cross z vector, this is what it does. It satisfies a few things. First is that y cross z is orthogonal to x and z. So for example, say I had, just for simplicity, I put y and z in the same plane. Sorry. Y and z are in the same plane. I will tell it the y and z plane over there. And if I cross them, the vector that I get is coming into the x now. It's an x vector. And it comes kind of out of, if this was a piece of paper, it would come out of the piece of paper. So that's one thing it says. It says it's orthogonal. Next is it satisfies the right-hand rule. So if we go back to here, and we're taking y cross z, we would put our hand along y this way, and then fold our fingers to z, and our thumb shows us the direction that it comes out. So in this case, if it was on a piece of paper, we have y cross z, and it shows that our x comes out of the piece of paper. That's what the right-hand rule is. It also satisfies this equation. And I'll be honest, I don't know where this equation came from. He didn't really tell us. So we have the magnitude of y cross z equals the magnitude of x times the magnitude of y times sine theta. This equation will come into play a little bit later in just a second. This shows that parallel vectors equal 0. And why? Because a parallel vector means that the degree between those vectors is either 180 degrees or 0 degrees, which means that sine goes to 0, which makes all of this 0. So that's one thing, that parallel vectors cannot be crossed with each other. So that means that I can't take I cross I because those are in the same direction. I can't even take I cross negative I. Also, different directions, but it's 180 degrees difference, and so that's going to make it 0. It also says that if a vector is 0, the cross product would be 0. And that makes sense because if y, the magnitude of y is 0, then this will all 0 out. Okay, very good. Now let's go to the properties of cross products that can maybe help us to make some proofs. First thing is it's anti-commutative, which is opposite of a dot product where it is commutative. So this, and I already made a mistake here, and I'll show you why in just a second. Y cross z is equal to negative z cross y. Not to be mistaken, and I have an example here. Say I have I cross j. It does not equal negative I cross j. So you can't just take I cross j and then negative I cross j. That comes out to be a k there. I cross j is k. And a negative I cross j is just a negative k. And that is not true. To make it equal each other, it needs to be I cross j equals j cross negative I or negative j cross I. And that comes out to be k and then k, because the negative will make it the opposite. And also switching them will make it the opposite. And so it's important to know the order of cross products really does matter. Okay? Let's look at more cross products. Okay, so another property is that scalars can be taken out. So here I've got alpha multiplied by the y vector cross beta multiplied by the z vector. And it equals alpha, beta, and multiplied by y cross z. And so we can take the constants out, the scalars out. So this is helpful, and I thought of an example where we could do this. Say we're crossing this, and I don't want to have to multiply 20 by 4 and 2 and 10 by 12 and all that stuff, all that big math. Just in a reason for simplifying, what I could do is I could take out a scalar and simplify it, and then I have a much simpler cross product, just multiplied by 10. Why does that work? It is possible, and if we go back to our equation on the last page, because, let's just go to it. We have an x magnitude and a y magnitude multiplied by a sine theta. And so think, what were to happen if I were to put a scalar right here, multiplied by those things? Would it change the direction? The answer is no. The scalars I put here or here or here won't even touch this this angle right here, because the angle has to be within the sine. And so there's no operation or scalar that will do that will change my direction. So that's why you can kind of pull scalars out, because it does not change the direction. Okay, and last property is that it's distributive. But we got to be careful of how we distribute here. I noticed that when you have a w cross and then a y vector plus a z vector, you can just distribute it, but it's important that you still have the w in front of the y and the w in front of the z, because the w is in front of the y plus z here. So you could do the opposite as well. And if you have the y plus z cross w here, then when you distribute, it's just as important to make sure that the y is in front of the w and the z is in front of the w. We know because it's anti-commutative that the order of the cross product really does matter. It'll change your answer from being negative and positive. Other than changing it from negative to positive, I'm not sure how much it'll change. But in the certain order of when you do the cross product, negative and positives could make a big difference because you're adding and subtracting between vectors. So, how do we know how to do a cross product? This is interesting. So in class, he did the lemma of the cross product of crossing. And he did A cross B, and if A equals that, and if B equals that, and he FOILed it all out, and he took what each thing equaled, and he came out to this, that A2B3 minus A3B2, I in that direction, this in that direction, this in that direction. You can pause, and if you want to take a longer look at that. This was a lot of work that we probably won't memorize and or do. That's really tedious. That sucks. So I'd rather talk about how he did it, how we will probably usually do vectors, is with a determinant, which we can break this out into smaller determinants where we can solve easily. So how you solve this is it's draw an x starting from the left side, just like reading. So a times d minus b times c. A times d minus b times c. Dotted line minus the solid line. So that changes just a little bit. First thing to know is that we don't want to forget this minus sign in front of the j. Just because of how it all works, j is negative. I'm not entirely sure exactly why. He didn't say that either. So when we solve for, when we're solving for j, we got to make sure that our x is just backwards, that's all. So for example, we have here, if we wanted to solve for k, we have I cross j, top left to bottom, minus 2 times, I believe that's a 2 right there. Or it could be, yeah, 2. And I think that's a negative 2 actually. Negative 2. And that will give us k. When we solve for j, that means we're not using j, and we're going to use it backwards because it's a negative, a backwards x. So we start from the top right and the top left. Negative 2 times negative 2 minus 1 times negative 3. And then solve for I, we just do 2 times negative 3. I think that's a 3, actually, not negative 3. And then negative 2 times 1. Top left to the right. Make sure you minus that correctly. All right. Change of direction from cross products. He showed us what we can kind of do, and probably where we're going in the future. Where we're going in the future is probably called a triple scalar product, which I think forms some sort of shape, 3D shape, where you take the dot product of a cross product. And so I think that forms some sort of shape, which is interesting, but we don't know that yet. So right now he just told us the area of a parallelogram, where if you have any two vectors, so a vector and a b vector, and you put them tip to tail, and if you say you doubled it, so you had another b vector here and another a vector there, what shape you've created is a parallelogram. And so this distance from, say, an invisible b there to that corner right there in the shape of a parallelogram is going to be equal to this. Forms a right triangle, and it's going to be equal to the a vector times the magnitude of a vector times the sine of theta, if theta is right there, and we get that length. And we know that the area of a parallelogram is just the base times the height. Base times the height. So we get that height based off of a times sine of theta, magnitude of a times sine of theta. And then to get the rest of the area, we multiply it just by b, which is that length. So we get this equation, magnitude of a sine theta times b, or magnitude of a, magnitude of b times sine theta, which, and from the front page, that is equal to our cross product. So it's interesting that when we have a parallelogram, the area is going to be just the cross product of the two vectors. Okay, that was that lecture. Hope you enjoyed. Thanks for watching.